This video is for the first lesson for Chapter 3. In this chapter, we're going to take a look at work, energy, and also momentum, where we'll be focusing on collisions. Today, for the first day, we're going to be taking a look at just how to calculate work. And in all of the stories, the force is going to be constant. It might be at a weird angle, but at least it's going to be constant in size. Here we go, off into Chapter 3, all about energy and momentum. First topic is indeed all about work. And in physics, work is just the quantity we use to measure the effort that is put into some sort of task. Some things I can tell you about work. It's a scalar. It is not a vector. We will not be putting north, south, east, or west onto the ends of our answers when we go to calculate the work. The abbreviation for the quantity is just a capital W. And the units are joules, named after Joule, so it's a capital J. And here is the definition. This is the first time when we're actually starting to multiply vectors together. We've now got a dot product, and we talked about this a little bit back in Chapter 1, but it's probably worth doing a little quick look back at our notes back from Chapter 1. So I'm just going to pull up some notes from Chapter 1 that you've already got. Multiplying vectors. When we were talking about dot products, we said if you're multiplying two things together, yeah, we are. Here it's force and distance, actually. But in our notes from Chapter 1, we said, well, it could just be like A and B. You would want to multiply those two things together. So we'll multiply the force and the distance together. But we're also going to throw in there a cosine of the angle in between the force and the distance. We looked at a couple of examples in there. When things line up perfectly, you'd have a cosine of 0, and a cosine of 0 is a 1. So it doesn't change the answer at all. And in that story back in Chapter 1, it left it at 40. If you were carrying the box and walking sideways, when those two vectors, forces and displacements, are at 90 degrees to each other, cosine of 90 is 0. So work will not actually work out for you. Well, you'll get a value of 0 when you have the force and the displacement at 90 degrees to each other. Okay, so we've had those notes before. Let's try a couple out here. For today, unlike the next lesson, the work is going to be calculated on forces that are completely constant. They are not growing or shrinking in size. They might be at funny angles, but at least they're going to be steady in size. So first example, let's take a look at a box here. We're just going to look at the stranger examples and see how they actually play out. So here's a bit of a strange one. The box is actually experiencing a force to the right, but it's moving to the left. You might wonder, well, how would that ever happen? Well, maybe it was moving to the left already quite fast, and then you were using this force to slow it down, to stop it. So it can happen where you've got this anti-alignment, where they're anti-parallel with each other. So when we go to do this calculation, I want to show you this two different ways, kind of a Physics 12 approach and a Physics 11 approach, and you can compare the two. And there'll be times when the old Physics 11 approach might be quicker, but overall I think you'll like the Physics 12 approach. So on the left, here's the Physics 12 approach. You would just say, okay, 12 times 4 times the cosine of 180. In Physics 11, we would have said, oh, the displacement's backwards. One of those vectors is backwards, and we would have installed our own minus sign in there. Well, the cosine of 180 installs that minus sign for you. It is a value of -1. Either way, we're going to get an answer of -48 joules. So again, for the next couple of examples, we'll do Physics 12 on the left and then the old Physics 11 on the right. Okay, this one. This was the Mr. Heinrich gently pulling on the cat, trying to get it to walk across the floor, and it was just kind of sliding. What if there's a force at an angle and the object actually moves beautifully sideways, perhaps across the floor? So the plan, well, in Physics 11, we would have said, oh, you got to take that force and resolve it into its components and find out how much of it goes sideways. And you'd have to think about the trigonometry. Not anymore. If you're willing to just trust the dot product, we can do it this way. Right? Over here's the old school Physics 11 way, right? Got to imagine how much of the force is parallel in order to get it to work. So the new way, you just go, yep, 18 times 5, times the cosine of 30, because that's the angle between the two vectors when you put them tail to tail. In grade 11, we would have had to have thought about the SOHCAHTOA, the right angle trigonometry, and realized that, yeah, we can get the x component by going 18 cos 30. Sure, it's the exact same calculation, right? You look at it and there's a cosine in there. What I'm suggesting to you is you don't have to think about it anymore. You can just say, yep, trust the dot product, and it'll do all the thinking for you. So that answer in the end ends up being 78 joules, and that one's all done. So that one had a bit of a strange looking force. It was constant, but it was at a funny angle. Here's a story where the displacement's at a funny angle. Don't laugh at the clip art, it's all I could find. Imagine this is not a basketball player that's shooting. Imagine they're just going, look at this great basketball, and they're walking up this ramp, right? They're holding the basketball up, right, applying a force up on it so it doesn't fall on them. If that is a basketball, it's awfully heavy. It's more like a medicine ball. But anyways, they're applying a force up at 24. Well, they walk diagonally 8. So 2 different ways to do this. You can trust the dot product, just let it do its thing. Or you can say, well, the force is okay, but I might have to take the displacement and resolve it into parts and find out how much of the displacement is parallel with that F. If you go with the new way, the kind of the grade 12 way of thinking about it, you can just say, well, you know what? Angles in a corner add to 90. So if that's 20 degrees here, got to get to 90, then all the way up into there, that's going to be 70. As soon as you can see that, then you're in business. Right? So we can just go 24 times 8 times the cosine of 70. We don't have to do any thinking. The old way, you'd have to sit there and go, okay, got to resolve the 8, break it up into its parts, and then go from there. Final answer for that one ends up being 66 joules. Okay, a couple more here. These ones, they're not just going to offer you the force and offer you the displacement. We're going to have to put a little effort into finding them. Find the work required to drag the box at a steady speed of 12 meters per second for 3 minutes. All right, well, when they say steady speed, right, that's telling me that we're not accelerating. So that's telling me that the net force is actually equal to 0. And that means that you will have to pull on that box when you do your work. You'll be pulling perhaps to the right, making it go to the right. But you'll be battling against friction. And it will be a battle with no winners. There will be a perfect tie there. Once this thing is up to speed, up to that 12 meters per second, then a pull that's exactly equal to friction will be all that you need to keep it going, because objects in motion stay in motion, right, with that acceleration of 0. So the applied force is going to be in this story to the right, and the displacement, I'm assuming, is to the right as well. No issues there with the dot product. We're actually going to be putting in a cosine of 0. But what I am going to do is I'm going to use my knowledge of finding forces of sliding friction to help me calculate the size of the FA. So you will see me focusing on the friction force. I'm not trying to find the work done by it, but I am focusing on the work done by the applied force. I'm just saying that the applied force is equal in size to that friction force. So here we go. Work is force times distance. The applied force to the right, displacement to the right, things are great. They line up. But then what I'm going to do is say, all right, give me a moment. I'm just going to algebraically, just with my arithmetic here, figure out how big this applied force is by looking at the friction force. And I want the net force to be 0, so I know that they're the same size. It is sliding, so it is perfectly fair to use mu times the normal force, right? For sliding friction, that's always true. And this object is moving at a steady pace. So we can just go with v times t. We won't have to add on a 1/2 at squared term. That's the final example of the day. Okay, here we go. Got mu, and then mg would be the size of my Fn. And then over here is the calculation of the distance, 12 meters per second for 3 minutes, for 180 seconds. Done. Clean up the sig figs here, and the story's finished. So some key things on this one. We were actually looking at the work done by the applied force, and it's to the right. And again, I'm assuming that the displacement's to the right, so there's no worry about the cosine, right? It would be actually like throwing on here a cosine of 0 degrees. We are kind of cheating a little bit. We're using the friction force size to calculate the applied force size. In the final example, the applied force will not equal the friction force because we want this thing to go faster and faster and faster. So the last example here is going to be a little bit more involved. Here it is. An applied force accelerates a 70 kilogram box from rest up to 12 meters per second, and it does it pretty quickly in 3 seconds as it travels up this 20-degree hill that's got some stickiness to it. Coefficient of friction, sliding friction, is 0.12. We have to have a pretty impressive applied force here. It's not okay for it to just equal friction. For one thing, it's also fighting the hill. It's going to be fighting that mg sine theta. And we don't want a tie. We actually want the applied force to win that battle against friction and the slippery part of gravity because we want it to accelerate. So it's probably worth doing a nice little free body diagram here. Applied force will be up the hill. Now, what other forces have we got? Well, we got gravity going down. Great. But that never works really well for playing around with ramps. So let's go and break this thing up into a couple parts, into a crush and a slide. So we don't have to worry about the mg anymore. We can think about those two. And then we've got our normal force, which we'll choose to be the same size as the mg cos theta, the crushing part of gravity. And then there's going to be some friction. And if it's sliding up the hill, then the friction will be back down the hill. Mu times the normal force. Mu times not mg, but mg cos theta. All right, now remember, it's not going to be a tie. This applied force here is actually going to be better than the combination of friction and the slippery part of gravity, because we don't want a steady pace. We want an acceleration to happen here. So before I go and do any work calculations, I'm going to just see if I can figure out my dynamics and my kinematics. So kinematics, I know it starts from rest, and I know the final velocity needs to hit 12, and it's got to get there in 3 seconds. Got a couple things missing. How far does it go and what the acceleration is? I'm going to need both of those. So you would just go and spend a minute or two and find both of those. In either order, it does not really matter. So I noticed that I could find the acceleration. I actually used VF of 12 equals VI of 0 plus missing A times time of 3. Very, very quickly, I noticed that the acceleration had to be 4. For the displacement, I actually trusted that new acceleration number that I found and said, okay, got a VI of 0, time of 3, 1/2, acceleration of 4, time of 3 squared. I found that the displacement was 18. It does go 18 meters up the hill. Going to need both of those for the calculations we're going to do. So sometimes you have to do that. You have to go and just do some kinematics in order to figure out some missing kinematic values. Looking at the dynamics, looking at F net, the total force, equals mass times acceleration. Looking back, total force, hey, it's a battle between FA, friction, and the slippery part of gravity. So let's just go and tell F net that. I've got a winning FA, fighting a slippery part of gravity, and fighting some friction. And it's going to win. We don't want it to be a 0 net force. Don't cancel the m's, although there are m's in all of these terms. There's no m in the FA term, so you're stuck with the m's. Now, throwing some values in. This is one time when it's probably worth it to write each line out in your notes, because we're going to need all of these numbers in a minute. So here I am just doing the raw calculation. It looks like all I'm interested in is the FA, but actually I want to see these numbers. The slippery part of gravity is 234, 235-ish. The friction is around 77. And the net force, which is not really an actual force, it's just an idea of combining all of the forces, that's 280. Okay, well, the arithmetic slides into place pretty nicely. And using that idea of making sure we hit a net force of 280, we can see that the applied force needs to be around 592. Now we're going to go and calculate work, but we're going to do a few of them. We're going to do a few different work calculations. We're going to look at a few different forces out there and see what they're doing. So let's start off with the work done by the person. Right? Work generally is force dotted with displacement. So we could go, okay, applied force dotted with displacement. We're going to need to think about the angle between the applied force and the displacement. So this thing does displace its way up the hill, right? It goes this way. So it looks like those are beautifully aligned in our picture. So, okay, all right, here we go. We're going to have a 592 Newton applied force, 18 meters, and a cosine of 0, because we do have that beautiful alignment between the person pushing and the way that it goes. The answer, I'm going to give it to you a couple of different ways. Here's one with just way too many sig figs, but I want to show you something, and I don't want any round off errors in the end. And then here would be the answer that I would put down on a test or an assignment. It's got 3 sig figs, so it satisfies our rules. But there's actually there are actually a few other works that we can calculate. Work done by friction. You might think, what? What does that mean? Yeah, I want to know how much friction helps us get this box up the hill and going fast. And you're probably correctly thinking, well, it doesn't help. Great. What does the physics say about that? And the physics is going to say that it doesn't help. Looking back at the picture, what I can see is that friction right here is anti-aligned with the displacement. right? So it definitely doesn't help me get up the hill. No problem. The physics will know that, right? We've got a friction force of 77, the box goes 18, and there's the anti-alignment between the displacement and the force. So that picks up a minus sign, and the answer is, if you want to go right down to the joule, 1,392 joules. Okay, so far so good. What about this one? What about the work done by gravity? This one has a couple of different ways that people like to calculate it. They both give the same answer if you're careful. So I got to go back and look at the picture. Trying to figure out the angle here between gravity force and the displacement. You have two choices. The displacement definitely goes up the hill. Some people say, hey, let's just look at the mg sine theta. It's interesting. It kind of lines up with the hill. And don't worry about the mg cos theta because it's perpendicular. And when forces and displacements are perpendicular, they can do no work. And so some people say, let's look at this force, that displacement, and the angle's 180. And that works great. Other people say, well, can't I go back to the actual true gravity force, which is bigger and straight down, and then talk about the whole angle in here, which actually ends up being like 110 degrees? And the answer is you bet you can, right? Either way works just as well. So I'm going to put them both down here. So work done by gravity, you can say, well, I want to go with the slippery part of 234 times the displacement times the anti-alignment, the cosine of 180, no problem. Or you can go, no, the full mg is 686, 18 meters for the displacement at 110 degree angle. And if that's the way you see it, fantastic. Either way, you're going to get this number. A negative sign telling you that if you didn't already know, gravity is not going to help you get this box up the hill. Now, I guess you could ask the question, what about the normal force? What kind of work does it do? Well, it's perpendicular to the displacement, so it doesn't do anything at all. You can, though, ask this question. What's the work done by the net force? What we would call the net work, the overall work. Now remember, net force does not actually mean a force. It's not really there. It's just a bookkeeping thing talking about all the real forces that are there, like gravity and friction and the person. But it is a fair question to say, well, what does that all add up to? If I've got the net force being the total, can I talk about the net work, the total amount of work? And the answer is sure, you absolutely can. Some people like to look at it as being this kind of idea combination bookkeeping net force of 280 times the 18 and the perfect alignment. And other people say, well, can't I just add all of the works that I've been seeing so far? And the answer is you can do either of those. They're both going to be the same thing. And it works out to 5,040 joules. Now, next day, we're going to start to take actually it's 2 days down the road, we're going to start to take a close look at conservation of energy. And we're going to ask the question, well, if we've got all of the works adding up to 5,040, some are positive, big positive 10,000 here, and some are negative, and you get this 5,040, what is that 5,040 doing? What's it accomplishing? And it turns out in this story, it's actually increasing the moving energy, the kinetic energy. So this is just a little foreshadowing for where we're going to go, and then in a couple of days' time, down on lesson 3, turns out when we go from no speed at all up to a speed of 12, the kinetic energy that you're going to hit is 5,040. So it's not a coincidence. That's exactly what's happening there. The overall work in this story is actually increasing the kinetic energy of the object. And that is the end of our first day. All of the calculations here today have had forces that are steady in size. And that will change in our next lesson where the forces might change in size.